Now, this is the fourth part of Stiffness Matrix video. So in this video, we will explain, we will see how to solve this particular example using Stiffness Matrix method. So again, this is a two-span continuous beam and moment of inertia of both span is varying. First span, moment of inertia is I, and second span, moment of inertia is 3I. And this is the first span is subjected to point load at the center, and second span BC is subjected to a uniform distributed load of 24 kilonewton meter. Then analyze this beam using stiffness matrix method and draw bending moment diagram. So the first is determine the displacement matrix. Determine displacement matrix, that is delta matrix. So for this, obtain a degree of freedom. Okay, so determine the degree of freedom of the structure. So to calculate the degree of freedom, remove the loading and just show the structure only. So it is a continuous span with a supports A, B, and C. So at B support, at A support, this is a fixed support. Okay, so this is a fixed support. So therefore, at fixed support, possible displacement is equals to 0. Okay, so the fixed support degree of freedom is always equals to 0. So B support is a roller support, So where possible displacement is only rotation. Okay, because this roller support offers only one reaction. Roller support offers only vertical reaction, and therefore vertical displacement is not possible. But horizontal displacement is also not possible. Why? Because this particular loading is a gravity loading, vertical loading. So therefore, vertical displacement not possible, horizontal displacement is not possible. So only possible is the rotation. Okay, so this is a rotational degree of freedom at B support. Similarly, at C support, in the same case as a B support, here the rotation degree of freedom is possible. Okay, so in all, there are two degrees of freedom. One is at B and one second is at a C point. And both are rotational displacements. So at then assign the number, give the numbers. So here the rotational degree of freedom, assign the number as a 1, and at C point, the rotational displacement, assign the coordinate as number 2. So we can write then displacement matrix as there will be two elements. So this is the first coordinate. This is the first coordinate. So that is at coordinate 1. What is the rotational displacement? So it is a theta B is the unknown number 1. And this is the coordinate number 2 at this point. So what is the unknown displacement is theta C. So in displacement matrix, there will be two unknown displacements. One is theta B at coordinate 1 and theta C at coordinate 2. Then second is that now the load matrix. Now the load matrix. To generate load matrix, determine the fixed end moments. Due to loading, determine the fixed end moments. So there are two span. First is, this is the first span, this is the second span. So on the first span, the load is at the center. On the first span, the load is at a center. So this moment will be WL by 8. Okay, this will be WL by 8. This moment will be equal to again WL by 8. Then on the second span, there is a uniform distributed load. So therefore, MBC will be equal to WL square by 12, and this will be again WL square by 12. Now, these are the fixed end moments. To calculate the fixed end moments, our assumption is that we are assuming each span as the fixed beam. Okay. And therefore, so these are the separate fixed beam subjected to point load at the center. This is the separate fixed beam subjected to UDL. So these are the formulas, and the signs are positive, negative in the sense clockwise movement is positive, anti-clockwise movements are negative. Then elements in the load matrix. Okay, so this is there are two elements. So this is the restraining forces or the end moments at coordinate 1. Okay, now coordinate 1 is at B point. Coordinate 1 is a B point here. So there are two moments. First is clockwise movement MBA and anti-clockwise movement MBC. So it is a plus 62.5 and minus 72. These are the two moments. Okay. Then this is the coordinate number 2. Second element is at a coordinate number 2. So it is MCB now. So MCB is how much? MCB is a clockwise 72. So in that is equation number 2 is a load matrix. The first element is minus 9.5 at coordinate 1 and 72 at coordinate 2. Then generate the stiffness matrix. Now I will not explain this stiffness matrix because already in the case of in my previous videos, part number 3 and part number 2, I have in detail explained about how to generate the stiffness matrix. This is just a continuation. Only change and variation in this part is that there is a different moment of inertia. Part 2 is moment of inertia is 3I. So therefore, while calculating the displacement, while calculating the element, wherever the second part comes, whenever the second part moment of inertia is EI term comes, so at that place you just substitute as a 3EI. For example, this is for part 1, whose moment of inertia is only EI. Okay, but this is for the second part, so therefore substitute just as a 3I. This is only the change. Okay, so since there are two coordinates are there, so there will be a 2 columns. Size of the matrix will be 2 by 2. So equation 3 is the required stiffness matrix. Then use the equilibrium equation, that is step number 4. Step number 4, that is load matrix plus K matrix into delta matrix equals to 0. So this is the load matrix, that is equation number 2. Then this is the stiffness matrix, that means equation number 3. And this is the displacement matrix, that is equation number 1. So is equals to 0. Then do the multiplication of K matrix and delta matrix, and then take this particular part on the right side, and that is whatever the form of the equation here matrix for convert into simultaneous equation. So these are the two simultaneous equation in which there are two unknowns, EI into theta B and EI into theta C. So solve these two simultaneous equation and determine the value of EI into theta B and EI into theta C. Okay, so here one answer is EI into theta B is equals to 19.56. And similarly, now we here the EI into theta C is not determined, not shown, but we can determine easily. That is, substitute this value of EI into theta B in any of this one equation. So the slope at the C point is easily we can get. So we'll get. Now here, interestingly, the answer of this slope is positive. So that means whatever the assumption made initially, so we have assumed the coordinate 1 as a clockwise. That is, we have assumed this particular slope, this particular coordinate or this particular slope to be clockwise, and this also slope at C point is also clockwise, and therefore when the answer of this, the unknown displacement theta B, the answer is also positive. That means the slope at this point is correct. Our assumption is correct. Slope is positive here, clockwise here, and the slope at C point is also a clockwise. Then once the value of EI into theta B and EI into theta C is known, then by using slope deflection equation, now apply slope deflection equation and determine the moments at the ends. So the final moments are, so this is the first slope deflection equation, this is the second slope deflection equation, and this is the third slope deflection equation. Okay, so for BC span, so for BC span where the C support is the simple support, so we can use a modified slope deflection equation. So my intention here, my objective is not to explain, not to focus on the slope deflection equation, only how to generate, how to get these values of this unknown displacement using stiffness matrix is the main focus of the objective. Otherwise, this is assumed that you know all the slope deflection part. So after this, we have to use the slope deflection equations. So here for MBC, we have to use a modified slope deflection equation, and whether the answers are correct or not, we can check. That is, at the common joint B is there. So at B point, the equilibrium equation is MBA plus MBC must be equal to 0. Now it is coming. So therefore, answer is this equations are, the values are correct. Then using these particular values, plot the bending moment diagram. Okay, so this is the end of this example. Thank you.